this video, we'll talk about how should we think about restricting this relationship between U and X. Okay, so one idea could be that we could assume that U and X are uncorrelated in the population, which is to say that the correlation between our dependent variables and our error is equal to 0. Now, zero correlation really implies that there is no linear dependence. Okay, so zero correlation basically says there is no linear dependence. But it could be possible that even if the correlation of X and U is 0, that we might find that the correlation between X squared and U is not equal to 0. Or the correlation between X cubed and U is not equal to 0. Okay, so even if this holds, this may not be true. So this is a simplistic assumption, and sometimes a simple assumption like this can make statistical analysis more difficult. Okay, so a better assumption is to talk about the expected value of U given X. Okay, and this is better because U and X, both U and X are random variables, and we can really always define a conditional distribution of U given any value of X. Okay, so we can think about what is the expected value of U given X, and we want that to be equal to the expected value of U for all values of X, and we'll see what that means. But here we're trying to say that the expected value of U is not dependent on X. So we're saying that U is mean independent of X. Okay, so for all values of X, no matter what X is, the expected value of U across all slices of the population is equal to the average value of U over the entire population. So this condition right here basically says that the average value of U is the same across all slices of the population and is equal to the average value of U over the entire population. Okay, and we can do this because we can define conditional distributions of U given X. So let's assume here that what we didn't account for in our wage education example is ability. So maybe U contained some other factors that could affect wages, and this could be something like ability, right? So we want to basically say that the expected value of U given X equals the expected value of U. So we're basically saying that if the expected value of ability, whatever that is, the expected value of ability given 8 years of education, right? X is education. This equals the expected value of ability given 12 years of education, and this equals the expected value of ability given 16 years of education. You can keep writing this, but more generally, this is what it means, right? That the expected value of ability given any X is equal to the expected value of ability in the population, right? But you might think that this assumption might be certainly false, right? Because you might think that, well, people choose their education level sometimes based on ability. Okay, if you believe that, maybe this assumption is false. Okay. Similarly, in our land quality example, we can think about the model yield equals beta naught plus beta 1 fertilizer plus U. And U contains factors such as land quality, right? So we're basically saying, suppose U is land quality and X is fertilizer amount, then the expected value of U given X equals the expected value of U if fertilizer amounts are chosen independently of land quality. So you're basically not discriminating between land that is more fertile versus land that is less fertile. You are basically giving everybody fertilizer, or every plot of land fertilizer, and that is independently chosen. And you're not considering land quality. Okay, so this assumption can be reasonable, but it really is assuming that fertilizer amounts are chosen at random. Okay. So combining this assumption, which is sort of significant, right, with this assumption of normalization that we said, that the expected value of U is equal to 0, right, gives rise to this assumption here, which says that the expected value of U given X is equal to 0 for all values of X. And this assumption is what we use a lot in econometrics, and this is called the zero conditional mean assumption. Okay, so when we take this to the simple linear regression model, right, and you put the expectations operator on this entire linear regression model, we get the following. We get that the expected value of y given x equals beta naught. This was a constant, so the expected value of a constant is itself, plus beta 1x, right? The expected value of x given x is just x, plus the expected value of u given x, right? So if you simplify this, you can say that this is just equal to beta naught plus beta 1x, because this becomes 0. Okay, and so here what we have here is we basically have a population regression function, which says that the expected value of y given x equals beta naught plus beta 1x. Okay, and let's think about this. So here we have a diagram that's showing you x on the x-axis, y on the y-axis, and this is showing you the population regression function. So this is showing you this line, the straight line here is the expected value of y given x, which is just equal to beta naught plus beta 1x. Okay. Okay, now the straight line that you saw in this graph is the population regression function, and it is giving you the conditional distribution of y at different values of x. Okay, so in the graph, we basically showed you 3 different values of x. Okay, so for a given value of x, we can see a range of y values. Okay, because there is a distribution in the population. So let's turn to an example to understand this a little bit better. What do we mean by this, the expectations operator that we are applying to this simple linear regression model? So let's think about, as an econometrician, maybe you're interested in predicting college GPA by some data on high school GPA. Okay, so maybe there is a population of students attending university, and we somehow know, we have some sort of estimate on how college GPA relates to high school GPA. Okay, so even though this sounds unrealistic, maybe your past performance is not a predictor of your current or future performance, for now, just assume that we know exactly what beta naught and beta 1 are. Okay, so here we're saying that the expected value of y is college GPA, given x is high school GPA, equals 1.5 plus 0.5 high school GPA. Okay, so if this were true for a second, if you believe this to be true, then in case if for somebody high school GPA is 3.6, if high school GPA is 3.6, we can plug in the numbers and calculate what the college GPA is. We can predict what college GPA is. Okay. Now you might say that, well, maybe anyone with a high school GPA of 3.6 is probably not going to be doing going to be performing at 3.3. But the point here is that if we had estimated a model like this, right, and if this was true, 3.3 is representing the average value of the college GPA within the slice of the population we're dealing with, within that sample that we have. Okay, so within the slice of the population with high school GPA of 3.6. Okay, so remember that when we are talking about regression is always explaining effects of explanatory variables. So basically explaining the effects of x on the average outcomes of y. Okay, this is important, that this is capturing the average effects.